Introduction. The procedure was simple for this lab. We were to drop a magnet through a tube of aluminum foil with the north side pointing down. I determined which end was north by using the app on my phone from Lab 3. The physics principles demonstrated on this lab are Faraday's law, the Biot-Savart law, Lenz's law, and Newton's third law. Faraday's law states that when flux changes there is an induced current, with Lenz's law specifying that the induced current is in the opposite direction. The Biot-Savart law is demonstrated in this lab by the force on the current carrying ring, and Newton's third law is demonstrated by the fact that the force on the magnet by the tube is the same as the force on the tube by the magnet. All of these principles work together to show why the magnet takes longer to fall through the tube of aluminum foil than it does just to fall normally through air. The main result from this lab is that the average fall time experimentally is 0.664 seconds. However, the computational model produces a result of 1.124 seconds fall time. This slide shows each of my 5 trials' time and the average time, along with a picture of the lab setup on the right. To create my computational model, the first part was to set up the geometry of the tube, based off of measurements I took from my actual tube of aluminum foil. Then the numerical parameters were established, and the tube of aluminum foil was created by creating rings stacked along the y-axis. Then the properties of the magnet were established. The bar magnet itself was created as a cylinder, and the initial conditions were set for the magnet's velocity to be 0 and the time to be 0. Then I inserted my dipole B function, which calculates the magnetic field of the bar magnet. Next, I wrote a function to calculate the d flux over d time for each ring due to the falling magnet. So this is calculating for each ring the d flux over d time. So the derivative of the flux with respect to time. Then the simulation loop is created through a series of while loops and if statements. And then next, the force of gravity is calculated by multiplying mass times gravity, and then the negative sign is there because it is falling down, which has been established as the negative direction in this simulation. And then d flux is calculated for one of the rings due to the falling magnet, and then it's eventually calculated for all of the rings in this for loop. The rest of the function goes on to calculate the magnetic field at the ring, and then finally the actual current for each ring. Then, the position of the magnet is updated, and this updated position at the very end is used to calculate the time that the magnet spends in the tube, which is at the end showing exit time minus enter time to calculate the final time. The graph that is produced shows a generally exponential decay model, and again shows my final result of 1.124 seconds in the tube. So what if the resistivity of the conductor were reduced as close as possible to 0? The current in the ring would be much bigger if the resistance was lower, and this would lead to the magnet staying in the tube for longer, because the current in the ring is what is actually causing the magnet to stay in the tube for longer. If the current were bigger, the magnet would stay for longer. If holes or slots were cut into the tube, how would this affect the model? If the slots were cut horizontally, it wouldn't change anything, because the model is already a series of horizontal rings down the y-axis. But if the slots were cut vertically, the rings would not retain current well, and the magnetic force would decrease, which would mean that my model would be less accurate and would produce a longer fall time than would actually happen. The clockwise versus counterclockwise currents. The magnetic flux is down, and since blue is on the bottom, it induces a counterclockwise current against the clockwise current in the tube. Red is on top and corresponds to clockwise current. Since blue is on the bottom and I know that it's the north end of the magnet, I can use my right hand rule to determine the counterclockwise and clockwise correlations between red and blue. What if I flipped the magnet and dropped it? The current and induced currents would now go in opposite directions. That's because the north and south would be flipped. The time comparison. And experimentally, the fall time was 0.664 seconds versus my computational model, the fall time is 1.124 seconds. I believe this is because in the computational model, the induced current is working perfectly to keep the magnet in the tube, whereas in real life there are other forces. It's an exponential decay plot, which means the force weakens as the magnet moves down the tube.